What if I told you the universe is threaded with invisible strands of pure energy cosmic strings, remnants from the very moment of creation, thinner than an atom yet stretching across billions of light years? These ghostly filaments, woven into the fabric of spacetime itself, are more than just cosmic curiosities. They could hold the keys to unlocking secrets of the early universe, rewriting the laws of physics as we know them. Picture this: remnants from the first trillionth of a second after the Big Bang, surviving undetected for over 13.8 billion years. If that doesn't send a shiver down your spine, consider this: these strings could warp space and time so intensely, they might create closed loops capable of time travel or even act as portals to other dimensions. This isn't science fiction, it's the cutting edge of cosmology. Think of cosmic strings as cosmic scars, frozen in the aftermath of the universe's violent birth. When the newborn cosmos cooled, these threads of energy, unimaginably dense, unthinkably ancient, were left behind like cosmic leftovers, vibrating with the echoes of creation. Scientists suspect they might be the missing link to understanding everything from dark matter to the very structure of reality. And here's the wildest part: we might finally be on the verge of detecting them. So why does this matter to you? Because unraveling the mystery of cosmic strings could redefine our place in the cosmos. Imagine harnessing their power to probe the earliest moments of existence, or bending spacetime itself to peer into realms beyond our universe. This isn't just about physics, it's about pushing the boundaries of human curiosity, about daring to ask, what if the universe is far stranger than we ever dreamed? Buckle up, because today we're diving deep into one of the most mind-bending phenomena in existence. By the end of this journey, you'll see the universe and your place in it in a whole new light. To grasp the sheer strangeness of cosmic strings, try picturing the universe in its earliest moments, a seething, unfathomably hot soup of energy. As it expanded and cooled, tiny imperfections formed in the fabric of spacetime itself, like cracks spreading through ice as it freezes. These defects didn't smooth out. Instead, they stretched into unimaginably long, incredibly thin filaments, cosmic strings, each one a flaw woven into the very structure of reality. Think of spacetime as a vast, elastic bedsheet. If you crumple it and then stretch it flat again, tiny wrinkles remain. Cosmic strings are like those wrinkles, but with mind-bending properties. They're not made of matter, they're pure energy, denser than anything in existence, yet so thin that if one crossed our solar system, you might never notice. Their gravity is so intense they could bend light like a lens, creating double images of distant galaxies. And if two strings crossed, they might snap and reconnect in violent bursts of gravitational waves rippling through the cosmos. What makes them truly bizarre is their scale. A single cosmic string could stretch across the entire observable universe, yet be no wider than a proton. They're relics of symmetry, breaking moments when the fundamental forces of nature split apart during the universe's birth. Like cosmic fossils, they preserve clues about physics at energies so high, no particle accelerator could ever recreate them. Some theories even suggest these strings could be vibrating at frequencies that dictate the shape of the universe itself. The wildest part, we might be floating through a web of these invisible threads right now, their gravity subtly tugging at stars and galaxies. If we could find one, it wouldn't just be a discovery, it'd be a time machine, letting us peer directly into the universe's first chaotic moments. To understand how cosmic strings came to be, we have to rewind the clock to a time when the universe was hotter and denser than the core of a star. In those first moments after the Big Bang, all the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single, seamless force. But as the universe expanded and cooled, it underwent dramatic shifts, like water freezing into ice or steam condensing into droplets. These cosmic phase transitions weren't smooth. Instead, they left behind cracks in spacetime itself, defects we now call cosmic strings. Picture a pot of water boiling violently, then suddenly cooling. Bubbles form, merge, and pop, but sometimes the boundaries between them don't align perfectly, leaving behind tiny imperfections. Now imagine that happening to the very fabric of reality. When the early universe cooled, regions of space froze into different configurations, and where these regions met, the mismatch created cosmic strings, threads of trapped energy like knots in a cosmic rope. This process, known as symmetry breaking, is similar to how the Higgs field gives particles mass, but instead of creating mass, it left behind these bizarre relics. Some theories suggest cosmic strings might be as old as time itself, vibrating with echoes from the universe's first trillionth of a second. And because they formed when spacetime was still malleable, their sheer density means they could still be out there, stretching across the cosmos like invisible fault lines. Detecting them would be like finding a fossil from the dawn of time. Unlike black holes or neutron stars, cosmic strings aren't made of matter, they're pure energy, distortions in spacetime itself. If one passed through Earth, it might leave no visible trace, yet its gravitational pull could distort distant starlight or even warp the very fabric of time around it. The hunt for these elusive threads isn't just about proving they exist, it's about unlocking a window into the universe's most violent and mysterious beginnings. Cosmic strings and black holes might both twist the fabric of spacetime, but they do it in ways so radically different. It's like comparing a razor's edge to a bottomless whirlpool. Picture a black hole, a crushing singularity where gravity is so strong not even light can escape. It's a cosmic trapdoor with an event horizon, a point of no return. Now imagine a cosmic string, infinitely thin, yet pulsing with enough tension to rival the entire mass of a star. It doesn't swallow matter or light like a black hole. Instead, it slices through spacetime like a wire through cheese, warping everything around it without a single particle crossing its path. The key difference lies in their structure. A black hole is a collapsed star, a knot of matter so dense it punches a hole in spacetime. But a cosmic string, it's not made of matter at all. It's a flaw in the universe's geometry, a relic of the Big Bang's aftermath. While black holes drag spacetime inward, cosmic strings stretch it taut, bending light and time around them in bizarre ways. If you orbited a black hole, you'd eventually spiral into oblivion. But if you circled a cosmic string, you might find yourself completing a full loop faster than expected, because spacetime itself would be twisted into a helix around it. Here's where it gets even stranger. Black holes hide their secrets behind event horizons, but cosmic strings have no such curtain. Their influence is naked, written in the distorted paths of galaxies and the faint whispers of gravitational waves. Two strings crossing could create a cataclysmic snap, sending ripples through the cosmos, a signature we might detect with telescopes. And unlike black holes, which evaporate over eons, cosmic strings could be immortal, threading the universe since its first moments. They're not destroyers, but sculptors, subtly shaping the cosmos with their invisible fingers. So while black holes dominate the cosmic horror stories, cosmic strings are the universe's quiet architects. One crushes, the other bends, one conceals, the other reveals, and if we ever find one, it won't just change physics, it'll rewrite the story of how spacetime itself was woven. Finding a cosmic string would be like searching for a ghost with a flashlight in an endless void, because these threads aren't just invisible, they're almost undetectable by design. Imagine trying to spot a strand 1 billion times thinner than a human hair, stretching clear across the universe. Their width is so minuscule, smaller than the nucleus of an atom, that even if one sliced straight through Earth, we might never feel it. Yet their gravitational footprint, that's where things get interesting. Unlike stars or planets, cosmic strings don't emit light or radiation. They're stealthy, leaving no trail unless they distort spacetime itself. But here's the clue. Their immense density, packing more mass than a mountain range into a thread thinner than a proton, creates a gravitational pull so intense it can bend light like a magnifying glass. This effect, called gravitational lensing, is our best shot at spotting them. Picture a cosmic string drifting between us and a distant galaxy. The string's gravity would warp the galaxy's light, splitting its image into twin mirages or stretching it into a faint, luminous arc. Astronomers already use this trick to find dark matter, but with cosmic strings, the distortion would be razor-sharp, a telltale flaw in the cosmic lens. Even wilder, some strings might hum. Theoretical models suggest that as these relics vibrate, they could emit faint bursts of gravitational waves, ripples in spacetime detectable by observatories like LIGO. It'd be like hearing the echo of a plucked guitar string from the dawn of time. But there's a catch. These signals would be whisper-soft, drowned out by the cosmic noise of colliding black holes and neutron stars. To catch them, we'd need instruments sensitive enough to pick up a spacetime tremor from billions of light years away. And then there's the dark horse of detection, cosmic microwave background radiation. If a string passed through the early universe, its gravitational tug might have left faint scars in this afterglow of the Big Bang. Subtle temperature fluctuations that telescopes like the James Webb could one day uncover. It's a long shot, but so was the idea of black holes a century ago. The hunt for cosmic strings isn't just about finding needles in a haystack. It's about realizing the haystack itself might be woven from threads we've yet to see. Gravitational waves are usually the domain of colliding black holes or merging neutron stars, violent, crushing events that send shockwaves through spacetime. But cosmic strings, they could rewrite the script entirely. When these filaments oscillate, snap, or collide, they don't just bend spacetime. They pluck it like a guitar string, sending out gravitational ripples with a signature unlike anything else in the cosmos. Picture a cosmic string vibrating at nearly the speed of light, its immense tension whipping spacetime into waves that could travel billions of years before reaching us. Or two strings crossing and reconnecting, releasing a burst of energy so sharp it would leave a distinct spike in gravitational wave detectors, a cosmic fingerprint etched into the fabric of reality. What makes these signals so special is their shape. Black hole mergers produce a familiar chirp, a rising frequency that peaks at collision. But a cosmic strings wave would be starkly different. A sudden, almost musical tone, like the ping of a snapped rubber band stretched across the universe. Some models even suggest these strings could create repeating patterns, a rhythmic hum from the same filament vibrating over eons. For scientists at observatories like LIGO or the future space-based LISA mission, catching one of these signals wouldn't just be another detection. It'd be like uncovering a message from the universe's infancy, written in the language of spacetime itself. The real challenge, distinguishing these whispers from the cosmic noise. Gravitational wave detectors are already tuning into collisions across the universe, but a cosmic string signal would be subtler, more fleeting. It might last mere milliseconds or linger as a faint, steady drone. And if we do spot one, the implications would be staggering. Unlike black holes, which form from dying stars, cosmic strings are primordial. Their waves would carry untouched information about the universe's first moments. They could reveal how spacetime behaved at energies so extreme, no lab could ever recreate them. Think of it like this: every other gravitational wave source is a footnote in the universe's story. Cosmic strings, they're the opening paragraph, and if we learn to read their vibrations, we might finally understand how the cosmos wove itself together. Time doesn't flow evenly around a cosmic string. It twists, warps, and sometimes even folds back on itself. Imagine standing near one of these invisible threads where the fabric of reality is stretched so taut that time itself slows to a crawl. The closer you get, the more seconds drag like hours while the rest of the universe races ahead without you. This isn't just theoretical. A string's gravitational pull is so intense it could bend time into loops, creating what physicists call closed time-like curves, paths that circle back to their own starting point. In other words, time travel. Think of it like walking along a spiral staircase that somehow brings you back to the step you just left. Near a cosmic string, space-time isn't just curved, it's knotted. If you could orbit a string at the right speed, you might return to your starting point before you even left, breaking causality in ways that would make Einstein's head spin. Science fiction loves this idea: wormholes, time machines, paradoxes, but here's the shocker. The math actually checks out. General relativity allows for these bizarre loops under extreme conditions, and cosmic strings fit the bill perfectly. The catch: these time loops aren't stable or easy to navigate. A string's gravitational field is more like a cosmic blender than a gentle time warp. One wrong move and tidal forces could shred matter atom by atom. Even if you survived, the energy required to harness a string's time-bending effects would dwarf anything humanity could produce. But the mere possibility shakes the foundations of physics. If closed time-like curves exist, even as fragile, fleeting phenomena, they'd force us to rewrite the rules of cause and effect. Could information or even particles travel backward in time? Would paradoxes unravel reality, or does the universe have a way of smoothing out the wrinkles? Here's where it gets even weirder. Some theories suggest that cosmic strings might not just bend time, they could stitch together separate universes. Picture two parallel sheets of spacetime pressed together by a string's gravity. Under the right conditions, that contact point might become a bridge, a shortcut through higher dimensions. It's a concept straight out of speculative fiction, yet it emerges naturally from the equations. The universe's earliest moments were a playground for extreme physics, and cosmic strings are the last surviving witnesses. They're not just relics, they're portals to a deeper understanding of reality, where time isn't a straight line but a tangled web of possibilities. So while we might never ride a cosmic string into the past or hop between dimensions, their existence would prove that the universe is far stranger and far more malleable than we ever dared to imagine. The real question isn't just whether time loops are possible. It's what their existence would tell us about the fundamental nature of reality itself. Cosmic strings might be invisible, but their fingerprints could be all over one of cosmology's greatest mysteries: dark matter. Picture this: as these ancient threads vibrate and decay over eons, they could shed fragments of unimaginable density, particles so exotic they barely interact with light or matter. These remnants, drifting through the cosmos like cosmic dust, might just be the invisible glue holding galaxies together. Here's how it could work. When a cosmic string snaps or collapses, the energy tied up in its immense tension doesn't just vanish. Instead, it might transform into ultra-heavy particles, far stranger than anything in the standard model of physics. These particles wouldn't behave like ordinary matter. They'd be nearly ghostly, passing through stars and planets without a trace. Sound familiar? That's exactly how dark matter behaves. Some theories suggest these string-borne relics could account for the universe's missing mass, solving a puzzle that's baffled scientists for decades. Think of it like a frozen lake cracking in winter. As the ice splits, it leaves behind shards, some large, some microscopic. Cosmic strings could have fractured in a similar way, littering the cosmos with dark matter particles during the universe's fiery youth. Unlike traditional dark matter candidates, which require elaborate mechanisms to form, strings offer an elegant solution. Their decay products would naturally cluster around galaxies, tugged by gravity into the vast halos we detect today. But the implications go deeper. If dark matter came from strings, its distribution wouldn't be smooth. Instead, we'd find faint, filamentary structures, echoes of the original cosmic threads woven through the cosmos. Astronomers might already be seeing hints of this in the way galaxies clump along invisible lines like beads on a string. And here's the kicker: If dark matter carries the imprint of these primordial defects, it could explain why simulations of galaxy formation always seem to underestimate how tightly matter clumps together. Strings wouldn't just be relics, they'd be architects sculpting the universe's hidden skeleton. The real test, hunting for anomalies in the cosmos, regions where dark matter seems too dense, too sparse, or arranged in ways that defy conventional models. Telescopes like Euclid or the Vera Rubin Observatory could spot these irregularities, tracing them back to the violent demise of cosmic strings. And if we ever detect the gravitational waves from a string snapping, the timing might just match the birth of dark matter in the early universe. It's a radical idea, but that's the beauty of cosmic strings. They're not just leftovers from the Big Bang, they're potential keys to unlocking the universe's darkest secrets. If they're out there, woven into the fabric of reality, they might finally reveal why 95% of the cosmos remains invisible to us, and that would be more than a discovery. It'd be a revolution. The universe might be threaded with an invisible web far stranger than anything spiders could weave, a vast, dynamic network of cosmic strings stretching across billions of light years. Picture this, filaments of pure energy crisscrossing the cosmos, intersecting and intertwining like cosmic fibers in a tapestry that's been growing since the dawn of time. These aren't static relics, they're alive in their own way, vibrating, snapping, and reconnecting in an endless dance governed by the universe's deepest laws. Simulations of these string networks reveal a structure eerily reminiscent of neural pathways or the delicate veins of a leaf, a fractal-like pattern repeating on scales from galactic superclusters down to the quantum realm. When scientists model the early universe, they find that cosmic strings wouldn't just form as isolated threads. Instead, they'd emerge as a tangled hierarchy, with smaller loops breaking off from larger ones like droplets splintering from a waterfall. Over eons, gravity would tug these filaments into intricate webs, their intersections sparking bursts of gravitational waves, and their motion subtly shaping the distribution of matter. What's mesmerizing is how these networks evolve. Like a spider adjusting its web, the universe constantly reconfigures its stringy scaffolding. Loops shiver and decay, long filaments snap under their own tension, and new connections form in the aftermath. Some strings might stretch so far they'd weave through entire galaxy clusters, while others could curl into tight knots, vibrating at frequencies that hum across spacetime. If dark matter is tied to these strings, their ghostly webs could explain why galaxies aren't scattered randomly, but clustered along invisible threads, as if the cosmos itself is following a hidden blueprint. The most striking simulations suggest these networks could be self-sustaining, even self-repairing. When a string breaks, the energy released might spawn new filaments, perpetuating the web across cosmic time. And here's the kicker. If we could see this hidden architecture, it might reveal why the universe looks the way it does, with vast voids between galaxies and luminous clusters strung along filaments like pearls on a necklace. These strings wouldn't just be leftovers, they'd be the universe's silent architects, their gravitational fingerprints etched into everything from the birth of stars to the fate of superclusters. Detecting this web wouldn't just confirm their existence, it'd rewrite our understanding of cosmic structure. Telescopes scanning for gravitational lensing patterns or anomalies in the cosmic microwave background might one day trace the outlines of these threads, showing us the skeleton behind the visible universe. Until then, simulations are our best window into this hidden realm, painting a picture of a cosmos far more connected and far more intricate than we ever imagined. Hollywood loves cosmic strings, just not quite the way physicists do. Take Christopher Nolan's Interstellar, where the crew navigates a wormhole near Saturn to reach distant worlds. While the film nails the mind-bending visuals of warped spacetime, real cosmic strings wouldn't need a wormhole's entrance. They'd be the distortion, slicing through the galaxy like invisible razor wires with gravity so intense, they'd bend starlight into eerie double images. The movie trades scientific precision for spectacle. Understandable, because watching Matthew McConaughey orbit an infinitely thin thread for 3 hours wouldn't exactly pack theaters. Then there's Doctor Who, where the TARDIS gets tangled in time threads that unravel reality. The show brilliantly captures the surreal potential of strings, time loops, dimensional rifts, but glosses over the physics. Real cosmic strings don't glow or hum melodically. They'd be utterly invisible, detectable only by their gravitational grip. Yet the creative liberties work, turning abstract theory into adventures where the Doctor battles collapsing timelines. It's storytelling alchemy. Take a kernel of real science, sprinkle in fantasy, and voila, you've got a universe where strings are less astrophysics and more cosmic plot devices. Even Thor, Ragnarok dabbles in stringy lore, with the Bifrost Bridge echoing theories that cosmic strings could link distant parts of the universe. The film's Rainbow Road is pure Marvel magic, but the core idea isn't far off. Some models suggest strings might create stable paths through spacetime, shortcuts for the bold or foolhardy to traverse the cosmos. Of course, in reality, approaching one would spaghettify you faster than Hela's wrath, but hey, superheroes get a pass. The trend, pop culture cherry picks the coolest bits of string theory, time travel, portals, universe-ending snaps, while sidestepping the equations. And that's okay. These depictions spark curiosity, nudging audiences to wonder, could this be real? The gap between science and fiction isn't a flaw, it's an invitation. After all, every fantastical portrayal of cosmic strings started with someone asking, what if? And that's where all great discoveries begin. So next time you see a cosmic string on screen, grin at the creative chaos, then go read the elusive papers that inspired it. The truth might lack lens flares, but it's far weirder. Stephen Hawking once made a startling prediction about cosmic strings. They might evaporate, not with a bang, but with a whisper of radiation, fading into the cosmic background like steam from a cup of tea. His work in the 1980s suggested these filaments, under certain conditions, could leak energy in the form of Hawking radiation, the same eerie glow he famously theorized black holes emit. But here's the twist. While black holes take eons to evaporate, cosmic strings might vanish far faster, their immense tension unraveling in bursts of high-energy particles. Hawking's calculations revealed something even more provocative. If cosmic strings exist, they could be our only shot at proving string theory, the controversial framework that suggests the universe's fundamental building blocks aren't particles, but tiny, vibrating strings of energy. The problem, those strings would be too small to detect directly, trillions of times tinier than an atom. But cosmic strings, they're the macroscale version, floating relics from the same primordial physics. Find one, and you've effectively found a smoking gun for string theory's boldest claims. His reasoning was brilliantly pragmatic. Cosmic strings, he argued, are the universe's loudest experiments. Their gravitational waves, lensing effects, and radiation signatures would carry imprints of higher dimensional physics, data we could never gather in a lab. Imagine stumbling upon a string snapping in deep space. The gravitational waves from that event wouldn't just ripple through space-time. They'd encode information about the hidden dimensions string theory predicts. It'd be like finding a fossil with DNA perfectly preserved, offering a direct glimpse into the laws that shaped reality. Yet Hawking's vision came with a caveat. Not all cosmic strings would behave this way. Some models suggest only certain types, so-called superconducting strings, could emit detectable radiation. These hypothetical variants wouldn't just warp spacetime, they'd carry electric currents stronger than lightning, lighting up the cosmos like neon signs. Spotting one would require telescopes tuned to the right frequency, hunting for unexplained cosmic sparks in the void. Decades later, Hawking's challenge still hangs in the air. If we ever detect a string's telltale signal, it won't just validate his work, it'll thrust us into a new era of physics, where the boundaries between theory and reality blur. Until then, his words echo. The universe's most elusive threads might also be its most revealing. Quantum mechanics and cosmic strings might seem worlds apart until you zoom in on the universe's first moments. Picture the infant cosmos, a seething quantum foam where particles flicker in and out of existence, driven by the wild energy of inflation. These fleeting quantum fluctuations, tiny ripples in the fabric of reality, could hold the secret to how cosmic strings formed. Here's how, when the universe expanded faster than light during inflation, those microscopic ripples didn't just fade away. They were stretched, magnified, and frozen into the fabric of spacetime itself, like wrinkles in a balloon smoothed out but never erased. Think of it like blowing bubbles in freezing air. As each bubble expands, tiny imperfections on its surface, dust motes or uneven patches, get locked in place as the thin film solidifies. Inflation did something similar to the quantum froth of the early universe. What started as random, subatomic jitters got stretched into cosmic-scale defects, cracks in spacetime that became the filaments we call cosmic strings. And just as no two bubbles freeze with identical patterns, no two regions of the universe cooled in perfect sync. Where the transitions between these regions didn't quite match up, strings were born, threads of trapped energy woven into the cosmos like stitches in a quilt. The math behind this is mind-bending. Quantum fluctuations operate on scales a billion times smaller than a proton, yet inflation's exponential expansion could have blown them up to astronomical sizes. Imagine plucking a guitar string so gently it barely vibrates, then suddenly stretching that string across the entire galaxy. The faintest whisper of quantum noise became the blueprint for structures that could wrap around the observable universe. This isn't just theoretical elegance, it's testable. If cosmic strings emerged from quantum fluctuations, their distribution today should carry faint echoes of those primordial patterns. Telescopes mapping the cosmic microwave background might one day spot the telltale imprints of strings in the faint temperature variations left over from the Big Bang. It'd be like finding fingerprints on a cosmic crime scene, evidence of quantum mechanics playing out on the grandest possible stage. What's astonishing is the sheer scale shift. Quantum physics governs the realm of the vanishingly small, while cosmic strings shape the universe on the largest scales. Yet here they are, inextricably linked, proof that the universe doesn't just contain mysteries but layers them, connecting the infinitesimal to the infinite. Those first chaotic moments didn't just birth particles and forces. They wove the very fabric of reality, leaving behind threads we're only now learning to trace. Cosmic strings aren't just relics, they're time capsules, sealed at the universe's birth and floating through the eons untouched. Imagine stumbling upon a perfectly preserved scroll from ancient Mesopotamia, its ink still fresh, its words whispering secrets of a forgotten empire. Now scale that up to cosmic proportions. These filaments could be the closest thing we have to a direct recording of the Big Bang's first chaotic moments, encoding conditions so extreme, no supercomputer or particle accelerator could ever recreate them. Think of the early universe as a seething plasma, hotter than 1,000,000,000,000 suns, where the fundamental forces hadn't yet split apart. As the cosmos expanded and cooled, that symmetry shattered, like water freezing into jagged ice, and the cracks became cosmic strings. But here's the miracle. Unlike ice, these flaws never melted. They've survived pristine for 13.8 billion years. Their structure, tension, even the way they vibrate, all of it is a snapshot of physics at energies a quadrillion times higher than the Large Hadron Collider can reach. It's as if the universe left us a voicemail from its first trillionth of a second, and we're just now figuring out how to play it. The comparison to archaeology runs deep. When scientists study ancient pottery, they analyze its composition to deduce the temperature of the kiln that fired it. Cosmic strings offer the same forensic potential. Their density, their interaction with space-time, even the gravitational waves they might emit, each property is a clue about the universe's formative energies. Some models suggest that strings formed during a phase transition so violent, it might have created not just one universe but a multiverse. If true, these filaments could be bridges to realities beyond our own, their very existence proof of cosmic siblings birthed in the same fiery instant. What's astonishing is how little they've changed. While stars explode and galaxies collide, cosmic strings drift on, indifferent to the chaos around them. They're like a fossilized ripple in a pond, capturing the exact moment a stone hit the water. Even their vibrations, if we could detect them, might carry echoes of quantum fluctuations from the universe's infancy. Picture a guitar string plucked at the dawn of time, still humming faintly today. That sound, translated into gravitational waves or lensed starlight, could reveal how spacetime itself behaved when everything was smaller than an atom. The stakes couldn't be higher. If we ever confirm a cosmic string's existence, it wouldn't just be a discovery. It'd be like cracking open a cosmic egg, spilling secrets we've only guessed at. Are there extra dimensions coiled around these threads? Did the universe undergo more than one Big Bang? The answers might be woven into their very fabric, waiting for us to read them. Until then, these filaments remain the universe's most tantalizing postcards from the edge of time itself. Two cosmic strings drifting through the void might seem harmless until they cross paths. The moment they collide, spacetime itself recoils like a plucked guitar string, releasing a cataclysmic burst of energy so intense it could outshine entire galaxies for a split second. Picture two infinitely thin wires, each carrying the mass of 1,000 suns, snapping and reconnecting with enough force to send shockwaves rippling across the cosmos. These aren't just collisions, they're cosmic fireworks, lighting up the darkness with gravitational sparks visible across billions of light years. When strings intersect, the laws of physics twist into knots. Unlike matter, which crunches or melts under pressure, these filaments don't break cleanly. Instead, they violently reconfigure, flinging off loops of pure spacetime curvature like sparks from a welder's torch. Some models suggest these loops could decay into a shower of high-energy particles, igniting gamma-ray bursts, the universe's most powerful explosions. Others propose the energy released might sculpt vast clouds of gas into newborn stars, seeding galaxies in their wake. Imagine a supernova on steroids, but instead of a dying star, the detonation comes from a flaw in reality itself snapping shut. The aftermath is even wilder. A colliding string network wouldn't just fade away, it'd leave behind a chaotic web of vibrating remnants. Some loops might shrink until they vanish in a puff of Hawking radiation. Others could stretch into new filaments, weaving fresh threads into the cosmic tapestry. And if dark matter is tied to these strings, the collisions might scatter it like shrapnel, clumping it into halos that dictate where galaxies form. Telescopes scanning the sky for gamma-ray flashes or gravitational wave chirps could be witnessing the echoes of these primordial battles, fought with spacetime as the battlefield. What's mesmerizing is the scale. A single string collision might briefly outshine a quasar, yet leave no visible trace, just a ripple in the cosmic microwave background or a flicker in a detector's data. It's the ultimate cosmic irony. The universe's most violent events could be hiding in plain sight, written in a language we're only now learning to read. Every snap, every collision, every decaying loop is a fossil of the universe's fiery youth, a reminder that even the fabric of reality isn't immune to fireworks. Cosmic strings might be more than just relics of our universe. They could be the stitching that holds the multiverse together. Picture reality not as a single sheet of space-time, but as a stack of membranes floating in a higher dimensional bulk, like pages in a cosmic book. According to string theory's boldest ideas, our entire universe could be one of these brains, with others hovering just out of reach in dimensions we can't perceive. And cosmic strings, they might be the threads tethering these brains together, or even frayed ends of a larger fabric that once connected them. Imagine two parallel universes drifting through the 11th dimension, separated by an infinitesimal gap. A cosmic string stretching between them could act like a cosmic zipper, binding them in ways that defy conventional physics. In some models, these strings are the remnants of collisions between brains' cosmic scars from when our universe brushed against another, leaving behind defects that still vibrate with the energy of that encounter. If that's true, then every time a string snaps or oscillates, it might not just send gravitational waves through our universe, it could be tugging on the fabric of a neighboring reality. The implications are dizzying. If strings anchor brains, they might create stable pathways between universes, not quite wormholes, but something stranger. Think of them as cosmic tightropes stretched across dimensions, where the laws of physics could shift dramatically from one step to the next. Some theories even suggest that dark matter, the invisible glue holding galaxies together, might be ordinary matter from a nearby brain leaking into ours through these strings. It's as if we're living in an apartment building where the walls are thinner than we thought, and the neighbor's radio is bleeding through. Here's where it gets wild. If a string connects to another brain, its gravitational influence wouldn't stop at the edge of our universe. It could warp spacetime in ways that leave detectable fingerprints, anomalies in galaxy rotation, or unexplained gravitational lensing that point to something beyond. Astronomers might already be seeing hints of this without realizing it. Those bizarre voids where matter seems too sparse, or filaments where galaxies cluster unnaturally. They could be shadows cast by strings tugging on our brain from another reality. The most radical possibility, strings might not just link universes, they could be the reason universes exist at all. In the ekpyrotic model, our cosmos began when two brains collided, igniting the Big Bang. Cosmic strings would be the frayed edges of that collision, like seams in a cosmic quilt. If that's true, then finding one wouldn't just rewrite physics. It'd prove we're part of something infinitely larger, a multiverse where every thread ties another story into existence. Until then, these strings remain the ultimate tantalizing maybe bridges to worlds we can't see, woven from the same stuff as creation itself. The energy locked inside a cosmic string could power civilizations for eons if we could ever tap into it. Picture a single filament thinner than a proton yet dense enough to rival the mass of a mountain range. The tension within is unimaginable. Some estimates suggest just 1 centimeter of string could contain more energy than all the nuclear weapons ever detonated combined. Harnessing that power would be like bottling a supernova. Futurists dream of wrapping these threads around Dyson spheres, their gravitational fields funneling raw spacetime energy into usable forms. The process would be perilous. Getting too close could rip matter apart atom by atom. But the payoff would rewrite the rules of physics. A civilization mastering string energy wouldn't just solve their power needs, they'd unlock the ability to manipulate spacetime itself. Then there's the ultimate sci-fi fantasy, warp drives. Cosmic strings don't just bend space, they twist it into knots, creating shortcuts that could make faster-than-light travel plausible without breaking Einstein's rules. General relativity allows for this. Imagine pinching spacetime between two strings, forming a bridge where the normal rules of distance don't apply. A ship could traverse light years in days by skirting the edge of these filaments, riding their gravitational contours like a surfer on a wave. The Alcubierre drive, that staple of interstellar fiction, it might pale next to the real thing. Strings could be nature's pre-built warp highways, threading the galaxy with hidden routes. Of course, the engineering challenges are staggering. Stabilizing a string's oscillations would require technology bordering on magic magnetic fields strong enough to tame a black hole, materials that don't yet exist. And the risks: one miscalculation could shred a ship into quantum confetti. But here's the tantalizing part: if cosmic strings exist, the universe has already done the heavy lifting. We wouldn't need to create warp bubbles, we just need to map them. The wildest speculation involves strings as cosmic reset buttons. Some theories suggest manipulating their immense energy could trigger localized mini-Big Bangs, birthing pocket universes or rewriting physical constants in controlled zones. It's the kind of power that blurs the line between physics and divinity. For now, these ideas live in the realm of equations and daydreams, but history shows humanity's wildest dreams often become tomorrow's tools. The first creatures to crawl onto land couldn't imagine spacecraft, yet here we are, reaching for the stars. Cosmic strings might be the next rung on that ladder. Whether they are keys to the cosmos or just cosmic yard art, one thing's certain. If we ever learn to dance with these threads, the universe will never look the same. The cosmic microwave background isn't just the oldest light in the universe, it's a fossilized snapshot of existence's first moments, and hidden within its faint glow might be the scars of cosmic strings dancing through the primordial dark. Picture this ancient light as a canvas painted when the universe was just 380,000 years old. Most of its imperfections, those tiny temperature fluctuations, are random, the result of quantum murmurs stretched to cosmic scales. But some anomalies defy explanation. Razor-thin cold spots, abrupt discontinuities where the temperature doesn't just vary but jumps, as if space-time itself had a hairline fracture. These could be the fingerprints of cosmic strings slicing through the infant cosmos, leaving kinks in reality that even time couldn't smooth out. Imagine dragging a needle through wet clay. The groove it leaves behind isn't random, it's sharp, linear, unmistakably artificial against nature's usual chaos. Cosmic strings would have carved similar furrows in the early universe's plasma. As they moved, their gravitational pull would have shoved matter aside, creating wake-like distortions in the CMB's temperature map. These wouldn't blend into the background's gentle undulations. Instead, they'd stand out like surgical incisions, straight-edged, colder trails cutting across the sky, visible only to telescopes sensitive enough to spot deviations as subtle as 1 part in 100,000. The Planck satellite's detailed maps of the CMB have already flagged a handful of these eerie linear features, regions where the temperature drops in ways that inflation alone can't explain. But the smoking gun might lie in polarization. When light scatters off charged particles, it becomes polarized, its waves aligned in specific directions. A cosmic strings passage would wrench this alignment into abrupt twists, imprinting spiral patterns on the CMB's polarization map like fingerprints on glass. These signatures, dubbed Kaiser-Stebbins effects, wouldn't just hint at strings, they'd reveal their speed, orientation, even their tension. It's the difference between spotting a shadow and seeing the object that cast it. Here's where things get tantalizing. Some of the most prominent CMB anomalies, like the infamous cold spot in the southern sky, have defied conventional explanation. Could they be the aftermath of a string loop collapsing, releasing a burst of energy that subtly cooled the surrounding plasma? Or perhaps the universe's large-scale structure, the way galaxies cluster along vast, filamentary superstructures, mirrors an underlying web of strings, their gravity seeding the cosmos' architecture. The next generation of CMB observatories, like the Simons Observatory or CMB S4, will hunt for these clues with unprecedented precision. What's mind-bending is the timescale. The CMB captures the universe before the first stars ignited, before atoms even formed. If strings left marks here, they've been hanging in plain sight for 13.8 billion years, waiting for us to decipher them. Finding one wouldn't just be a discovery, it'd be like uncovering a lost chapter from the universe's birth certificate, written in the language of space-time itself. And that chapter might hold answers to questions we haven't even thought to ask yet. Simulating cosmic strings is like trying to map an earthquake with a microscope. You need to see both the tectonic plates shifting and the individual cracks in the bedrock all at once. The problem starts with their mind-bending scale. These filaments stretch across billions of light years, yet their cores are thinner than a proton, operating by quantum rules we barely grasp. It's the ultimate multiscale puzzle. To model them accurately, supercomputers must juggle the physics of the infinitesimal and the cosmic simultaneously, a feat that pushes even the most advanced algorithms to their limits. Take the latest simulations where researchers feed equations into machines with the power of 1,000,000 laptops. Even with that firepower, compromises are inevitable. To capture the quantum behavior near a string's core, simulations shrink spacetime into a grid with steps smaller than an atom. But to track how these threads weave through the universe, the same grid must expand to encompass entire galaxy clusters. The result, a computational nightmare where tweaking one parameter, say, the string's tension, can send ripples through the model that take weeks to untangle. It's like building a sandcastle while the tide comes in. By the time you fine-tune the quantum details, the cosmic context has already shifted. The challenges don't stop there. Cosmic strings don't exist in isolation. They tangle, snap, and reconnect in a dynamic dance that defies classical physics. Simulating these interactions requires stitching together general relativity, which governs their gravity, with quantum field theory, which describes their energy. The equations for this are so complex, they often crash simulations outright. Some teams resort to approximations, like treating strings as one-dimensional lines rather than quantum objects, but even these shortcuts demand months of supercomputer time. The most ambitious attempts, like those run at the NSF's Frontier system, can simulate only fleeting snapshots, a tiny fraction of a string's lifespan before the math collapses into chaos. Yet the payoffs keep scientists hooked. Each simulation that doesn't crash reveals something startling: how strings might seed galaxy formation, why their gravitational waves differ from black holes, or how their decays could pepper the cosmos with dark matter. The latest breakthrough, a simulation that showed string networks remember their quantum origins, evolving in fractal patterns that echo their birth in the early universe. It's a glimpse into a hidden layer of reality, one where the universe's largest structures are knitted together by threads thinner than thought itself. The irony is delicious. To understand relics from the universe's simplest, most symmetric era, we need the most convoluted computations humanity can muster. But every crashed simulation, every tweaked parameter, brings us closer to answering a tantalizing question: what if the cosmos isn't just filled with strings but built on them? Cosmic inflation and cosmic strings might seem like rival theories, one describing the universe's explosive expansion, the other its tangled imperfections. But dig deeper, and you'll find they could be two sides of the same cosmic coin. The inflation model tells us the universe ballooned from subatomic to cosmic size in less than a trillionth of a second, smoothing out wrinkles in spacetime like a hot iron on fabric. Yet strings are the wrinkles inflation supposedly erased. So how can both ideas coexist? The answer lies in the messy aftermath of that hyper-expansion, where even the most elegant processes leave behind scars. Picture inflation as a cosmic reset button stretching space so rapidly that any pre-existing knots or kinks would have been diluted to near nothingness. But like a stretched sweater snagging on a nail, certain defects might have stubbornly persisted. Strings could be those snags, relics so tightly wound, not even inflation's relentless pull could smooth them away. Some theorists argue these filaments aren't contradictions to inflation at all, but its natural byproducts. When the inflationary field, the energy driving the expansion, finally decayed, it might have done so unevenly, like a freezing lake cracking in haphazard patterns. Those cracks, cosmic strings, frozen into existence as the universe transitioned from its ultra-fast expansion to a slower, steadier growth. But there's a wilder possibility. What if strings weren't just inflation's leftovers? What if they triggered it? Certain topological inflation models propose that an especially dense cosmic string, vibrating in the primordial chaos, could have warped spacetime so severely that it spawned a pocket of runaway expansion. Think of it like a seed crystal dropped into a supersaturated solution, suddenly making the whole thing solidify. One string's gravitational pull might have been the nudge that sent our universe inflating, making these filaments not just survivors of the Big Bang but its architects. The debate gets thornier when you consider observational evidence. Inflation predicts a near-perfectly smooth universe, while strings would have left faint but detectable irregularities. The cosmic microwave background, our snapshot of the infant cosmos, shows just enough anomalies, unexplained cold spots, sharp temperature jumps, to keep both ideas in play. Some physicists argue these quirks could be inflation's quantum fluctuations magnified to cosmic scales. Others see the fingerprints of strings, their gravitational wakes subtly disturbing the primordial plasma. The truth might lie in between, a hybrid model where inflation dominates but strings scribble in the margins like ripples on a pond that's mostly still. What's fascinating is how these theories push each other forward. Without inflation, strings might have been too densely packed, clashing with observations of the universe's large-scale structure. Without strings, inflation might seem too tidy, unable to explain certain cosmic oddities. Together, they form a richer story, one where the universe's birth wasn't just a single explosive moment, but a chaotic symphony of expansion, fragmentation, and leftover echoes. Whether strings are inflation's side effect or its catalyst, they remind us that even the most elegant theories need a little cosmic roughness to feel real. Discovering a cosmic string would be humanity's greatest scientific achievement until we're forced to ask, should we mess with it? Imagine standing at the edge of a cliff where one wrong step could unravel spacetime itself. These filaments aren't just cosmic curiosities, they're threads woven into the universe's fundamental fabric. Poking one could unleash consequences we can't predict: gravitational distortions rippling through the solar system, time dilation pockets forming unpredictably, or even triggering a catastrophic phase transition that rewrites the laws of physics in our corner of reality. This isn't just theoretical. In 2019, physicists simulated what might happen if a spacecraft interacted with a cosmic string. The results were unsettling. Even a gentle pluck could transfer enough energy to destabilize planetary orbits or amplify quantum fluctuations on a macroscopic scale. Picture dropping a pebble into a still pond, only the ripples don't fade. They grow, warping everything in their path. A real-world string encounter might behave similarly, its gravitational wake bending light years of space into funhouse mirrors. And if two strings were to snap under artificial stimulation, the resulting gravitational wave burst could outshine a supernova, flooding our detectors with noise, or worse, attracting attention from something beyond our understanding. History offers eerie parallels. When the first atomic bomb was tested, scientists secretly debated whether the explosion might ignite the atmosphere. They proceeded because the pursuit of knowledge often outpaces caution. With cosmic strings, the stakes are orders of magnitude higher. Unlike nuclear physics, we're dealing with phenomena that could affect causality itself. What if probing a string creates a closed time-like curve, accidentally sending information or objects backward in time? The ethical dilemma echoes Jurassic Park's warning, just because we can doesn't mean we should. Yet the allure is irresistible. Strings might hold energy sources capable of powering civilizations for millennia, or technologies that render interstellar travel trivial. The same filaments that could unravel reality might also be the keys to unlocking it. This tension between risk and revelation is what makes the dilemma so profoundly human. We've always pushed boundaries, from sailing off the edge of maps to splitting the atom. Cosmic strings are simply the newest frontier, testing whether our curiosity can coexist with humility. Perhaps the greatest risk isn't touching a string, but touching it blindly. Before we intervene, we'd need safeguards, simulations running centuries ahead, fail-safes to neutralize unintended effects, maybe even galactic-scale observatories to monitor fallout. Even then, some consequences might be inherently unpredictable. That's the haunting beauty of cosmic strings. They don't just challenge our technology, they challenge our wisdom. In the end, the question isn't whether we can harness them, it's whether we're ready for what happens when we do. Quantum entanglement, the bizarre phenomenon Einstein famously called spooky action at a distance, might have an even spookier explanation: cosmic strings threading the universe like invisible puppet strings. Picture two entangled particles instantaneously influencing each other across light years, as if space between them doesn't exist. Conventional physics struggles to explain this. But imagine if their connection isn't magic, just physics we haven't mapped yet. Enter cosmic strings. These primordial filaments could be weaving quantum particles into a hidden network, their immense gravitational fields creating shortcuts through spacetime that make entanglement seem effortless. Think of it like this: if two ants crawl on a crumpled sheet of paper, their paths might appear separate, until you smooth the paper and realize they were inches apart all along. Cosmic strings could be warping spacetime in similar ways, pressing distant points together in higher dimensions we can't perceive. When particles become entangled, they might not be communicating faster than light. They could simply be linked by a cosmic string's twisted geometry, whispering to each other through a spacetime wrinkle thinner than a thought. The math behind this is staggering. String theory models suggest vibrations along cosmic strings could transmit information between particles without breaking light speed limits. It's not teleportation, it's topology. These filaments wouldn't carry messages like a wire. They'd reconfigure reality itself, making entangled particles adjacent in ways our three-dimensional brains can't visualize. Some physicists speculate that every entangled pair in the universe might trace back to a shared string, vibrating in sync since the Big Bang. The implications: entanglement isn't an anomaly, it's evidence of the universe's hidden stitching. Yet the wildest twist isn't how strings could explain entanglement, it's what they'd imply about the universe's structure. If particles stay connected across cosmic distances via these threads, then the quantum realm and the galactic scale aren't separate domains. They're parts of a single tapestry woven together by defects left over from creation. Every time we measure entangled particles, we might be glimpsing the handiwork of the universe's first moments, a fingerprint of spacetime's original flaws. Of course, skepticism remains. No one's ever detected a cosmic string, let alone proved it mediates quantum links. But here's the provocative thought: if strings do underpin entanglement, finding one wouldn't just solve a quantum mystery. It'd reveal that the spookiness Einstein resisted was never spooky at all, just spacetime's secret geometry, humming beneath the surface of reality all along. The real test: future experiments might look for entanglement patterns that only strings could produce, correlations too precise, too geometrically ordered to stem from chance. Until then, the idea lingers like a half-remembered dream. What if the quantum threads we've been chasing were cosmic strings all along, tying the universe together one particle at a time? Not all physicists buy into cosmic strings. Some argue spacetime's fabric is woven from entirely different threads. Take loop quantum gravity, a radical alternative that swaps strings for tiny, interwoven loops of spacetime itself. Picture reality not as smooth fabric, but as a mesh of microscopic rings, each one a billion times smaller than an atom, knitted together into a dynamic network. These loops don't vibrate like strings, they connect, forming the very architecture of existence. In this model, cosmic strings aren't needed because spacetime's flaws aren't defects, they're the stitches holding everything together. The clash between string theory and loop quantum gravity boils down to scale. String theory imagines cosmic strings as relics of higher dimensional physics, while loops reject dimensions altogether, proposing that space emerges from relationships between these fundamental knots. Imagine the difference between a tapestry strings and a chainmail shirt. Loops, one's continuous with embedded flaws, the other discrete and self-supporting. Loop quantum gravity even suggests that black holes aren't singularities, but ultra-dense tangles where loops tighten into knots. If cosmic strings are cosmic scars, loops are cosmic atoms, the indivisible units of reality. Yet both theories share a startling similarity. They predict spacetime isn't smooth. Where loop quantum gravity sees pixelated grains, string theory offers vibrating filaments. Both frameworks also struggle with the same hurdle: lack of experimental proof. But here's where loops diverge sharply. They reject the multiverse entirely. No higher dimensions, no parallel brains, just spacetime quantized into its simplest possible form. It's a minimalist dream, but one that struggles to explain why cosmic strings' gravitational lensing effects might already be hiding in telescope data. Another rival, causal dynamical triangulation, takes a different tack. It simulates spacetime as a mosaic of tiny, triangular blocks that shift and rearrange over time. In this view, cosmic strings would be seams where these blocks align imperfectly like cracks in a tile floor. The theory's proponents argue it better explains the universe's large-scale smoothness without invoking strings at all. But like loop quantum gravity, it stumbles when confronting anomalies like the CMB's linear cold spots, which strings explain elegantly. The irony: these competing theories might all be glimpsing facets of the same truth. Just as light behaves as both particle and wave, spacetime could be loops and strings or something beyond both. The real breakthrough may come when we stop forcing the universe to fit our metaphors and let it reveal its own structure. Until then, cosmic strings remain the leading thread in a tapestry we've only begun to unravel. Hollywood loves turning cosmic strings into doomsday devices. Imagine a rogue filament slicing Earth in half or spontaneously birthing black holes. But the reality, these ancient threads are surprisingly indifferent to our tiny planet. First, the odds of a string intersecting Earth are astronomically low. Picture throwing a single hair into a hurricane and hoping it lands precisely on a speck of dust. That's roughly the scale we're dealing with. Even if one passed through, its width is so infinitesimal it'd slip between atoms unnoticed. No explosions, no apocalyptic tremors, just a whisper of gravity too faint to detect without equipment far beyond today's tech. The black hole factory myth stems from a kernel of truth. Cosmic strings are unimaginably dense. A kilometer-long segment could outweigh Mount Everest, but density alone doesn't create black holes. For that, you need matter compressed within a specific radius, the Schwarzschild limit. Strings fail this spectacularly. Their mass is spread along near infinite lengths, making them gravity's version of a stretched rubber band. Intense tension, but no crushing singularity. Even if two strings collided near Earth, the energy released would dissipate as gravitational waves, ripples harmless to anything except hypersensitive detectors like LIGO. Then there's the fear of strings unzipping spacetime. While their gravity does warp reality, the effect is localized and stable. A passing string might slightly alter time's flow in its immediate vicinity. Think microseconds over centuries, but it wouldn't unravel the cosmos. Compare it to a ship's wake, disruptive close by, but the ocean doesn't tear apart. The universe's space-time fabric is far more resilient than pop culture suggests. What about planetary orbits? Could a string's gravity fling Earth into chaos? Not likely. Their gravitational influence is linear, not spherical like a star or planet. You'd need to orbit within kilometers of one to feel substantial effects. And even then, the pull would be directional, like a cosmic tide nudging objects along the string's length rather than scattering them randomly. The real takeaway: cosmic strings are less existential threat and more cosmic, whether distant, fascinating, and utterly indifferent to us. If anything, they pose far less danger than asteroids or solar flares. Their true risk lies in what we don't yet understand. Unlike a Hollywood monster, their intrigue isn't in destruction, it's in the secrets they hold about the universe's birth. So next time you hear a doomsday theory, remember, the universe's oldest threads aren't here to end us. They're too busy being its quiet architects. The hunt for cosmic strings is about to enter a new era, one where telescopes don't just scan the skies but listen to the faintest whispers of spacetime itself. Leading the charge is LISA, the Laser Interferometer Space Antenna, a revolutionary mission slated to launch in the 2030s. Unlike ground-based detectors like LIGO, which catch the thunderous crashes of black holes, LISA will float in space as a trio of satellites linked by laser beams over millions of kilometers. This sprawling network will tune into the low-frequency hum of the cosmos, precisely the range where cosmic strings might pluck the fabric of reality. Imagine trying to hear a violin's note in a hurricane. That's the challenge of detecting a cosmic string's gravitational waves amid the cosmic noise. But LISA design is a game-changer. Its sensitivity could pick up the high-pitched ping of a string snapping billions of light-years away or the steady drone of a vibrating loop, signatures unmistakably different from black hole mergers. If strings exist, LISA won't just find them, it'll reveal their tension, their motion, even their age, like a forensic analyst reading the grooves on a bullet. Then there's the Square Kilometre Array, or SCAR, the most ambitious radio telescope ever conceived. Stretching across continents from Australia to South Africa, its thousands of antennas will map the universe in unprecedented detail. While LISA listens for spacetime's vibrations, SKA will search for strings' visual fingerprints, those telltale distortions in distant galaxies. A cosmic string warping light could split a quasar's image into twins or stretch a galaxy into a luminous arc. SKA's resolution is so sharp, it might spot these anomalies even if the string itself vanished eons ago, like finding a fossilized footprint in cosmic mud. But the real dark horse, pulsar timing arrays. These projects use rapidly spinning neutron stars, nature's most precise clocks, as a galaxy-scale gravitational wave detector. As pulses arrive with metronomic regularity, any slight deviations could signal a string's passage. Recent data from collaborations like NanoGrav has already hinted at a background hum of low-frequency waves, possibly from supermassive black holes or something stranger. Future upgrades could discern whether that hum carries the rhythmic cadence of cosmic strings vibrating in the void. The coming decades will test our boldest theories with tools once deemed impossible. From space-based interferometers to continent-spanning radio dishes, these missions aren't just hunting strings, they're probing the universe's foundations. And if they succeed, the discovery won't just fill textbooks, it'll rewrite them, turning speculation into fact and reminding us that the cosmos always has one more surprise up its sleeve. Cosmic strings aren't just relics, they're master keys, capable of unlocking some of the universe's deepest vaults. From the violent chaos of the Big Bang to the invisible grip of dark matter, these filaments could hold answers to questions that have haunted physicists for decades. Imagine decoding the universe's first trillionth of a second, not through mathematical models or particle colliders, but by studying defects woven into spacetime itself. Strings are cosmic time capsules, preserving energies and conditions so extreme, they dwarf anything our most advanced experiments can replicate. If we could tap into their secrets, we might finally understand why matter triumphed over antimatter, how the fundamental forces split apart, or even whether parallel universes lurk just beyond our perception. But the implications go deeper than origins. Strings could redefine our understanding of dark matter, not as a sea of invisible particles, but as the shattered remnants of these primordial threads. Picture dark matter halos around galaxies not as featureless clouds, but as intricate webs, their structure echoing the snap and decay of strings billions of years ago. The same filaments might explain anomalies in the cosmic microwave background, those faint scars in the universe's oldest light that hint at something beyond our current physics. Every unexplained ripple in spacetime, every gravitational wave that doesn't fit the mold strings could be the missing piece, connecting phenomena we once thought were unrelated. What's exhilarating is how much we don't know. The hunt for cosmic strings isn't just about confirming a theory, it's about peering into the unknown with fresh eyes. Every telescope scan, every gravitational wave detection, every simulation brings us closer to rewriting the story of reality. And if history teaches us anything, it's that the universe loves surprises. Who could have predicted black holes would become laboratories for quantum mechanics, or that the Higgs field would turn mass from a property into an interaction? Strings might be the next paradigm shift, waiting to append everything we thought we understood. So keep looking up and stay curious. The cosmos has a way of outshining even our wildest fiction. If threads thinner than atoms can warp time, hide dark matter, and stitch together dimensions, what other wonders are lurking in the void just beyond our grasp? The universe isn't done revealing itself, and neither are we.